with this question from the June 2022 paper. Okay, so we've done the effect of concentration change and the effect of temperature. So question 20.1 is about temperature. We already did that. Now we're going to go to 20.2. Okay, the equation below represents the reversible reaction that takes place when NO2 is converted to N2O4. It's okay, I heard you were writing tests. How did it go? How did it go? It's an old exam paper. No. Okay, it will be in the collection of old exam papers around about page 80 or something. Okay, you have it here. Okay, you can go check Google for the June 2022 exam. Okay, I believe it will still be in the PDF you got of the old exam papers. Okay, around about page 80. June 2022. So write down June 2022.
Thank you, ma'am.
Okay, so we have this equation below where NO2 is converted to N2O4. Initially, right, X moles of NO2 is our reactant, is sealed in a 1 cubic decimeter container at 350 Kelvin. When equilibrium is established at this temperature, there is 0.81 moles of N2O4, so our product present in the container. Write down the meaning of the term reversible reaction.
When the products can be converted back into...
Yes, when our products can be converted back into reactants. Now, 20.2.2, show that the equilibrium constant for this reaction is given by 0.81 divided by x minus 1.62 squared. Okay, our equilibrium constant, what is that? Kc. Okay. So we know our Kc value is the concentration of our products. Yes, divided by the reactants. Now, how are we going to get the concentration?
By substituting.
Okay.
Wait. Of the mole. The volume of 1 decimeter.
Yes. So first of all, our concentration is mole over volume. We have been given the mole of our product, and we have the volume, so our mole is just going to be the same as our concentration, right? Because we divide by 1. 2.2.2. Yes, write down the meaning of the term reversible reaction. We're looking at 20.2.2 now. Oh, this is 20.1.1. Okay, so it's the previous question's work. I'm going to make a new page for question 20.2. So we know our 20.2.2. Okay. Our Kc value will then be the concentration of the N2O4 divided by the concentration of NO2. But this equation is missing something. What is it missing? Hang on a second. Yes. Okay. So In our balanced equations, we have a 2 in front of our reactant. So we need to put the concentration to the power of 2. Yes, but I was trying to get one of you to answer instead of all of you. Okay, so let's look at the question again. These concentrations, when are they measured? These concentrations, right? Because there's a reaction or concentration changes. So when are these concentrations measured? What concentrations do we need to substitute in here?
One's
At equilibrium, right? So when our reaction is at equilibrium, that's the concentrations we need to substitute in here. So they tell us when equilibrium is established, it would be 0.81 moles of our product, right? So that we can substitute in just like that. But with our reactant, they only tell us there's X mole present at the beginning of the reaction. X moles present. So how are we going to figure out how many moles is present after the reaction? Mole table, thank you. So we have 2 NO2, which is in a reversible reaction with N2O4. So we know we have a 2-to-1 ratio. Then we have beginning, change, and end. So what we know so far is at the beginning we have X moles of our reactant. At the end we have 0.81 moles of our product. We know we start with 0 moles of our product, so we have to add 0.81. Okay. So now we need to figure out if this much product form, how much reactant was used. Yes, so we are going to take N2O4 times our stoichiometric coefficient, which would be 2/1, because there's a 1 in front. So that is going to give us 0.81 times 2, which is 1.62. So that means we used, okay, let me write this in another color. We used 1.62 moles of nitrogen gas. So this is X minus 1.62. So now we have moles, so we need to convert to concentration. It's? Okay, right, because we're in equilibrium. We're in a reversible reaction, which means there will always be something present of everything. All your reactants and all your products. At any given time, there will be some of each present. So we don't look at limiting reagents for this. Okay. So we have our mole of N2O4, which would be equal to our concentration divided by our volume. We have 0.81 moles, and we have a volume of 1 cubic decimeter. So our concentration is 0.81 moles per cubic decimeter. Okay, and now the mole for our NO2 is equal to the concentration over our volume. The moles is X minus 1.62 equals to our concentration divided by 1. So our concentration is still just X minus 1.62. You look confused. Why are you confused? Okay, so we calculated the moles, right? The moles we have at the end of the reaction when the reaction is in equilibrium. Okay, so with these, we first must calculate the concentration because we substitute the concentration into our Kc value. So before we can substitute, we must convert the moles to concentration. Now we can calculate our Kc value. Okay, so this will be 0.81 divided by x minus 1.62 squared.
And that's exactly.
Okay, okay, you two, are you writing this down? Okay, write it down for now and then go through the work. I know you've missed a few classes. I've also recorded some of the classes, so it will be uploaded to YouTube. The thing is, I don't have Wi-Fi at home, so I'll try to do it after school today. Okay, so that is question 20.2.2. Show that the equilibrium constant is given by this. Okay, now they tell us 0.79 moles of our product, so we'll highlight that in blue, is added to the equilibrium mixture. So what did we change?
Added. What to this product?
We changed the concentration of our product. Yes, I'm taking in all of your books.
What books? You didn't work in books then.
Yes, okay. Okay, so what I'm going to do is I'm just going to sign your books to make sure you actually work. So if you don't have your book here today, you bring it to me Monday. I don't see you guys on Monday, but you bring it to me so I can sign it. On Monday. I'll be in my class at first break. You come to me with your books. Okay. Okay, let's get back to the problem because you guys are getting really distracted and I'm trying to show you how this will be asked in an exam. Okay, so we are adding some of our products. So we are increasing the concentration of our product. So when the new equilibrium is established, it is found that the amount of NO2 is our reactant. Okay, so NO2 increased by 1.2 moles. Okay, after equilibrium. Now they ask us, calculate the value of X. So we have a new equilibrium, right? Okay, we changed the concentration. How are we going to solve for X? How? No, you just continue with that thought simultaneously. What are we going to equate together? Okay, hang on a second. Yes, back there.
Ma'am, okay, because we increase the concentration, the Kc is not affected at all. So we're going to equate the Kc of the old equilibrium with the Kc of the new equilibrium.
Yes, okay, so we have a change in concentration. So our Kc value remains constant. So this Kc value will be equal to our new Kc value. Okay. But how are we going to get our new Kc value?
We're going to work out the concentrations of the other molecules.
Yes, I'm going to do that now. Okay, we're going to create a new mole table. Okay, because we have changed some stuff now. So we start once again with N2O. No, we start with NO2. NO2. the 2 in front, and N2O4, which has a 2:1 ratio. So at the beginning of this reaction, this part of the reaction, when our new equilibrium is established, what do they tell us? They say 0.79 moles of our product is added. So we take the end value here and add some more. So that's 0.81 plus, what was it? 0.79. What? Okay.
Why don't you add the 0.7 at the change?
Not the beginning, at the change.
Okay, so because when we look at, let's go back to our concentration. Okay, so when we look at our concentration, when we add something, it's an instantaneous add before the reaction starts again to establish a new equilibrium. So it must be our beginning value. We must add it to our beginning value before the reaction starts again. Okay. Yes. Okay, and then for our NO2, we start with x minus 1.62. Okay, so now we increased the concentration of our reactant, our products, I mean. We increased the concentration. Yes. Yes.
So that solution of 7.9 is the original beginning for the
That is how much we added to the system.
solution is the original one.
The original one is the 0.81. Okay, that's how much we had at the end of our first equilibrium. Then we added some more. We added 0.79 to it. Yes. Okay, added with the new stuff we added. Okay, so let's see what else they said. Okay, when the new equilibrium is established, it is found that the amount of our reactant increased by 1.2 moles. Okay, so that means our change is 1.2 moles. So at the end, we would have x minus 0.42. Okay, do you guys understand this? Okay, so now we must figure out how much of our product was used, right? Okay, so we're going to have a negative here, right? Okay, you understand that? You're not confused because usually you have a plus with your product. Okay, so we increase the concentration of our product. Okay, that means our reverse reaction is favored. That means our products is used to make reagents. Okay, so we are going to working with the backwards reaction now. Okay, so now we know we add 1.2 moles of NO2, so that means if we want to figure out the moles of N2O4 added. Hi.
Can I quickly describe the force by giving Fatima the
Thank you.
On his way, you're digging to something to say.
gravity?
Okay, so the moles used of our N2O4 would be 1.2 times a half, because it's 1 to 2. You can divide by 2 as well. It's going to be the same, 0.6. So How much moles of N2O4 do we have left?
0. Oh, wait, 1.
Yeah, it's one.
1.
Yes.
A nice round number. Okay. So now we can determine our second Kc value. So let's name this one Kc1 and this one Kc2. So this is equal to the concentration of our N2O4 divided by the concentration of our NO2 squared. Okay, but as we know, because our volume is equal to 1 cubic decimeters, our concentration will be equal to our mole. Okay, so I'm not going to do this again. So, yes. So this is equal to 1 over x minus 0.42 squared. Now we can say our Kc1 is equal to Kc2. So this means 1 over x minus 0.42 squared is equal to 0.81 divided by x minus 1.62 squared. Okay, so can you solve this mathematically?
Break this first.
Yes. Okay, so we are going to cross multiply to have 0.81 times x minus 0.42 squared equals to x minus 1.62 squared. Okay, come. Okay, so go further on with solving for x.
Okay, so here, by, by 1,2 times by half. I don't understand why did you times by half?
Because it's our ratio of 1 to 2.
Okay, so after we get this 0,6, for here, to figure out the one now, can't you just say 0,81 minus 0,6?
Okay, but you must remember to add the 0.79
To add it to it.
to the 0.81. Because remember, we added this at the beginning. Okay, this is our change to increase the concentration of our products.
So it's 1,6.
Yes.
Oh, I see now.
Okay,
Thank you, ma'am.
no problem. Everyone whose bags must be judged. Second break behind the
Today's jail.
personnel room.
So
The anything but a school bag things. Okay.
must you use the formula, doesn't?
I think so. I think.
Ma'am, do you use the formula?
What formula?
Negative b.
The quadratic formula. Yes.
Oh, when you say what formula, why did you say that? What?
The quadratic formula. Yes.
Formula.
I remember it up. Are they gonna give us some kind of
Hell no.
In the exam.
Yeah.
Well, this was a June 2022 exam, so yes. It's obviously not for sure you are going to get a problem like this, but you can expect a problem like this where they test your math skills.
We still,
And then they are like keys.
but we still in COVID-19, it wasn't worse like that.
You guys can't blame COVID anymore.
COVID.
We can. We are the COVID kids. We are we did not know.
COVID kids. Yes, indeed.
Okay, so what's the quadratic formula?
It's negative b plus minus square root b square minus
I want to fall in.
over 2a. You didn't say that, doesn't?
I said that. I said about that. I said that.
Doesn't matter.
You can't see I'm pulling his leg. I know, wow, pose.
That's a rough
So we're gonna get two answers.
Of course, you're going to get two answers. So
So then, what is the value of this?
x is 12.417.
You are a different person.
Yeah.
You don't get a negative answer?
You know. You do. Why is it
Yes, good.
How is it 12?
It's saying math error.
Yeah.
Shame. Shame.
Is a what? Is a man? I don't know.
Dun, 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 dun.
Maybe this one. Negative. Ma'am, I can't see your numbers very well. What is the 5?
Now, the second number I get is 1.0519. I know this one's right, but
So which one are we going to use? Because that other one.
okay. So let's logically think about this, right? It's either 12 or 1 mole. I just want someone to check the values that I get.
Ma'am, I want in the middle is those two things 5 or 8.
5.
Yeah.
I got 12,4.
Same.
Okay, that doesn't matter. It's small decimal places that differ, but what did you get for your second value?
I get 1.0.
Okay, so we do get two positive values. Okay. Okay, so let Bontle just finish that calculation.
Yes, I get 12,42 for the first one.
Okay, so we have two values to choose from, right? It's either 12 or 1.05. So, first of all, what is x? What is our unit?
Wait, mole? No, decimeters.
It's low.
It's mole. So it's either 12 mole or 1 mole.
But guess what? It's 1 mole.
Okay, so let's see what makes the most sense. For us to have, let's see, if we put 1.05 in here, we're going to get a negative value, right? And we can't have a negative amount of mole, right? So our answer will be 12. Okay, so this is our right answer.
Now, can we please go to the question?
Yes, I'll go to the question.
It said something weird. Oh, I didn't.
Okay, so you see here they give a range. Your answer could have been 11.27 to 12.42.
Yo, that's a nice big range.
The first one, my first calculation that I did was I got 19 comma something. Actually,
Okay, so you guys good with this problem? Kind of.
I wanna look at
What do you want to see?
I wanna say can here. Why did you multiply by a half?
Because we have 1 over 2.
Oh,
Okay, it's our coefficient, right?
oh, okay.
That's everything we do with the multi-table. We do with this.
Oh, so this one is our product. This is our reactant. Why wasn't this one on top of this one? This one on top of this one.
Okay, because we have the 1.2 here, because they tell us that it's found that there's 1.2 moles more
More.
of
Inside
our
our
NO2.
Oh.
Yes, so we add the 1.2. Let's see what they say here. The amount of NO2 was increased by 1.2.
1.2.
So increased by 1.2, so plus 1.2.
You see?
Okay. Okay, I kind of get it. Okay, I kind of get it.
Okay, good. I'm glad. Okay, so this was a really difficult example, right? But you see, you guys understood what was going behind this example. You understood that if we increase the concentration of our products, that means our backwards reaction will be favored. So that means our reactants will become more, or reactants will become more. We add reactants, but we subtract products. Yes.
do you have hand lotion?
I don't. Sorry. Okay. So let's move on. Oh, I